Hello everyone, welcome back on the course of higher surveying, and now we are in the module 4, that is error accuracy and adjustments computation. Well, in the last 3 modules we have learned different aspects of the higher surveying. First was just an introduction, the second module was all about the reference frame, moreover it was about terrestrial reference frame, and third one was about astronomy and the time. Okay, so far we have learned how to develop a reference frame and how to develop a coordinate system to refer a point in 3 dimension. Let us look into the error. What's the error while locating a point or while measuring some quantity or variable? Let us go ahead. We have 5 lectures in this module. First is fundamental concepts of error, accuracy and error propagation that we are going to take today, and remaining 4 lectures we are going to take in the series. So these are the books. I would like to say here that first 2 books like Adjustment Computations, Spatial Data Analysis by C.D. Gilani and P.R. Wolf, as well as the second book, An Introduction to Error Analysis by John R. Taylor. Okay, both these books are quite new as well as they are available in market easily. However, remaining 3 books from here to here, you have to consult a library, and better option is to go to an institute library. Perhaps you will get these books there. Otherwise, it's very difficult to get these books, but I can say these 5 books are the Bible of adjustments computations as well as error and accuracy analysis. And secondly, they have a special flavor for higher surveying. So better to get hold of these books. At least you can get hold of first book, or you can go to some library. So let us start. What is an error? Okay, I start with simple terms. First term is observation. What do you mean by observation? Okay, let me give you an example. I am observing a raindrop in the air. It is falling from the cloud and reaching to the surface of earth. So I am observing it. I am observing this room. This room has one camera, one light, few other accessories. I am observing them. So what I am doing here? I am making them separate from the rest of the surrounding and trying to observe them very keenly, attentively, and that is what we call observation. Let us go to the next term, abstraction. Let us say I want to observe, or I want to measure, or I want to create an abstraction for some aspect. First example, that was the raindrop. The next example, I have a project here and I have an objective here that I want to lay down some tiles on this floor of this room. So what I need to do? I need to measure the area of this room. Okay, what's the purpose here? Purpose is, if I have the area of this room, I will buy some tiles of the same area so that I can do the flooring of this room. Now I have observed this room very carefully and it appears to me a rectangle. It appears. I do not know. I do not measure whether it is rectangle or slightly deviating from rectangle shape, but I assume because it is appearing to be. Well, so this is my observation. And abstraction is, I assume it to be a rectangle now. Why? Because I can see that angles are at 90 degree and there are 2 walls, so total 4 walls at 90 degree angle. So let us assume it to be rectangle, and as a result, if I measure length and width of this room, I can find out the area of the rectangle. So the abstraction is, this room is a rectangle. Rather, I can say I make the assumption of a rectangle shape for this room because I can simplify this problem and I can estimate the area of this room. Okay, what could be other shapes? It could be triangular, it could be circular, it could be pentagonal, octagonal, and so on. But in general, I have some knowledge, I have some experience or prejudging of the things. I know that rooms are generally made rectangle, and so I say that it's a rectangle only. It's not circular, it is not triangular, and I should not suspect this room to be other than a rectangle. So we have made the abstraction also. Now I want to do measurement. Okay, measurement is very simple. I am taking length and I am measuring the width. So while measuring the length or width, I know I have a tape. Let us say this is my tape, this pen, which is, let's say, 6 inches long. So if I use this 6 inches scale and I keep on measuring, what will happen? I can measure the length of the room or I can measure the width of the room in a straight manner. Okay, let us say there is a tape of 5 meters, right? And now if I stretch the tape between the two ends of a room along its length, I can measure its length. Well, that's a measurement. I hope that I am very clear about three terms: observations, abstraction and measurement. Let us go ahead. Now, while measuring, we have stage 1. And this stage 1, it is possible that by mistake I note something else or I speak something else to my colleague and he writes something else, or even I am speaking correct value, he is writing something else. So, there could be some carelessness from all the possible persons involved in the measurement process, and because of carelessness I am noting down or I am recording some wrong value, and this is what we call the mistake. Okay, understand that mistakes can be avoided with the help of carefulness or attentiveness. So, assume that we have not done any mistake, we have not committed any blunders, we do not have any gross error, which are basically three names of mistakes. So, we do not have gross error, mistakes or blunders in my observation. Fine, because I was enough careful while taking observations. And then I have also checked my observation later after recording whether I am correct or not. I found I was absolutely correct. Whatever the measurements was there, I have noted down those only. Okay, then stage 2 comes. Let us say I have a tape to measure the length of this room, but that tape was calibrated at 20 degrees centigrade. Unfortunately, the room temperature is 30 degrees centigrade. What will happen? Because of the 10 degree positive difference, tape will expand, and that expanded tape still have the same graduations: 1 centimeter, 2 centimeter, 3 centimeter and up to 5 meter. So, if I am measuring the length, which is let us say 2.3 meter at 20 degree centigrade, the tape, now it will be shown little less because tape has expanded and the graduations are still at the same place, or they have also expanded basically along with the tape. But now graduations are not modified according to the actual length of the tape, and as a result the tape will show me little less than 2.3 meter. Okay, but I know here that temperature is increased by 10 degrees centigrade and tape should expand because the material of the tape has these characteristics. And if I know the material characteristics, I know the temperature difference, I can find out what is the expansion in the tape length, and accordingly I can make the corrections. So, the moment I make some estimation of correction by some mathematical or physical rule, I call such errors as systematic errors. So, the errors caused by the temperature or higher temperature or could be lower temperature than the calibrated one is a systematic error due to temperature. Similarly, if I change other ambient conditions, let us say pressure, humidity and so on, that will be the other type of systematic errors, or I can say there are different type of systematic errors present. Okay, and now say that I have removed those systematic errors also. So, first I was careful, so I removed gross errors or blunders. Secondly, I was intelligent enough to remove the systematic errors also. But now at stage 3, still I will have some errors, and these errors are inevitable. Why? There could be a simple example here, and the first and simple example is, let us say you have a tape which is having centimeter marking, 1 centimeter, 2 centimeter, 3 centimeter and so on, and you try to measure the length of this room with that tape, and tape shows you, let us say this measurement 2.33. Okay, let us say this is the tape here and it is showing here 2.34. Okay, if you measure the length of the room and room length is coming somewhere here, what will you say for the length of the room? Let us take little higher estimate, call it 2.34 because I want to do the flooring. What will happen? Material will be little more for the flooring, but it will not be less. So, no problem, extra material I can throw away, I can afford to throw away that material. Just imagine the other situation. My contractor has done the work, complete flooring. Now again I want to measure because I want to make payments. I am little clever, intelligent than contractor. So what will I do? Now I will say it is 2.33 only. It is not 2.34 because while purchasing the material I was worried enough to have more material so that flooring should not be disturbed or flooring should be proper. So after flooring or after completion of the work, I want to save my money. So I am saying let us become little more intelligent than the contractor, person who has done the work, and I am claiming that it is 2.33. Okay, he is also a sharp man and he says no, it is 2.34. Fine. Then we make an agreement. Okay, let us assume that it is a kind of average of two values. Let us take 2.335, that is an average of two values, which is 2.33 plus 2.34 divided by 2. Not yours, not mine. Let us take the average. And we have agreed on meter distance of the length of this room. So now you have understood that we have committed error here, right? Someone may argue here, why 2.335? Why not 2.334? Can I claim or can that contractor claim it is correct value? Or can someone claim that this is correct value? Both are not correct. We cannot guarantee it. So the issue here is we are always committing some inevitable errors because of the limitation of the instrument. And this is the message here. Okay, someone can read it 2.331 also. There is nothing wrong. Why? Because someone can read 2.334, someone can say 2.335 or 2.336 also. But so we are committing some kind of errors here now, and they are inevitable in nature. And such errors are called random errors. So this is one of the source of the random error where we have limitation on the instrument. Okay, so let me just remove this here. Okay, and let us go ahead. So now I know that random errors are inevitable and I will have it in measurements. So what is random error? It is an inevitable uncertainty. Okay, they are experimental. That means if I conduct some experiment, if I take some measurement, they will come into the observations. Definitely they will come. Secondly, so I can write here a simple relationship. Let us say there is a true value is equal to observed value plus the error, or what we call it inevitable error. Let me call it error only, and it is basically the random error. This random error, I do not know what is the exact amount here, right? Secondly, we already know that we can never know the true value. We already know it from basic surveying. So the idea is by observing just an observed value here, this observed value, I cannot find out error or true value. So what can we do here? First of all, I cannot eliminate them because I do not know the amount of error. How can I eliminate? Systematic error, I know that what's the exact amount because it's following some physical rule or mathematical rule. I have developed that rule by experiments and I've removed it. But after removing all the systematic errors, these inevitable errors, basically they are so small and they are occurring randomly. I cannot do anything with that. So the idea is they are so small compared to the measured values. That means if I am measuring 2.33 meter, it could be of 1 centimeter, it could be of 1 millimeter, I am very small. So now let us look further. They are equally probable for positive and negative side. What's the meaning here? Errors, they are following the normal distribution. Okay, so idea here is, let's say this is some value of error here. So this is the probability shown by this curve. So this is the probability. So they have equal probability on both sides. That is this probability here and this probability here. Right? This is the negative value of error and this is the positive value of the error, same error, positive E or minus E. They have the same probability of occurring. And so this is giving me some hint here. Fine, I'll just tell you what is the hint. So now idea is as I know that I cannot measure the true value because I do not know what is the true error. But what can I do here? I can do only one thing. I can have some estimate of the largest possible error. Again, that will be an estimate, and then that estimate I can always consider to be on safer side, because if I consider what is the worst case possible value of an error, I can always know what could be the maximum possible error in measurements. And that is what we do. What we do, we try to find out some estimate of error, and then we find out the maximum possible error. How these characteristics of this normal distribution, they help me to do that. And that's the reason we always use this kind of assumption that errors are normally distributed. Moreover, it is also observed experimentally for a large number of observations, they follow normal distribution. So no worries, this assumption is quite valid and it is known from last 400 years or more. Okay, so let me give you some more example here. Now we have understood that we have the error in our measurement. So let us assume that there is a bag, and bag is full of cold drink bottles. Each bottle is completely wrapped around by a paper so that it is not visible that how much amount of cold drink is filled in the bottle. So I can say a bottle could be partially filled, it could be fully filled, or it could be empty also. So the empty bottle is complete error and the full bottle is the zero error. For partially filled bottle, the empty space is the error and the filled space is observation. Okay, the bag is full of such bottles, let's say infinite number of bottles, and you want to select one bottle to have a cold drink. Can you give me a guarantee that if you pick a bottle which you do not know, filled, empty or partially filled, will be as per your choice? That means it will be always completely full, or it will be partially full, only upper brim is not filled. Can you give me some guarantee over there? You are allowed to take only one bottle? I think you yourself will say no, because it is quite possible that you bring one bottle out of that and that bottle is completely empty. That is the maximum error and which is indicated here. But the probability is also less here. The probability is that you will end up with some observation, that is a bottle which partially filled. There are chances are high. So now you got the idea that yes, each and every observation have some error and they are random. That means the amount of unfilledness or the amount of emptiness in the bottle you do not know. So you do not know what's the error. It could be completely empty. It could be completely filled. Completely filled means it does not have any error, but that will be by chance if you get it. The message is very simple here. If you take one measurement, you cannot guarantee that it will be errorless. It could have random errors of large quantity. But I can guarantee you one thing. If you take a couple of bottles from that bag, chances are very high that you will have lot of errors, because you are taking a couple of observations, and then if you average them, you can minimize those errors. That means if you take the observations, this much filled, and so on, if you take the average of all the filled values, you will find out that you are reducing the overall value of the error, which is here in one bottle, another bottle, one more bottle, and so on. So if you take the average of all the observations, your errors will be minimized. And that is why we always take multiple observations, not the single observation. We do not rely on single observation. I hope that you can appreciate why do we take multiple measurements. Okay, when we take the multiple measurements, we have two ways of taking the observations. One is the replicated measurements and another is the repeated measurements. So when I take replicated measurements, it means the ambient conditions, let us say temperature or humidity, pressure or whatever, these ambient conditions are not changing over the time. So then I say I am taking replicated measurements. That means I am taking multiple measurements, but the ambient conditions are not changing. And because of that, I have certain advantages. I know that the random errors are there, but whatever situations are there, they are similar, they are same. But what if I take repeated measurements? That means my ambient conditions may change, which means let us say I am taking one observation by tape in the morning, 8 o'clock, when temperature is around 20 degrees centigrade. and I am taking the observation with the same tape in afternoon 2 o'clock when temperature is 45 degree in peak summer. So now you can understand that I am taking the repeated measurements, not the replicated measurement, and ambient conditions are changing. So these are the basic terms we should understand. Okay, in case of replicated measurement, I repeat that I am taking the multiple measurements at same time, same place and same ambient conditions. In case of repeated measurements, I am taking multiple measurements at different time, different location or in different ambient conditions. But in either case of repeated or replicated measurements, I should have some kind of theory that can tell me what's the quality of the measurement. So the quality of measurement is very important, and as we told that since we cannot estimate the individual true error in each observation, what will I do? I will take some estimate of the overall error, or I will have some kind of estimate for the largest possible value, so that I can always know what could be the worst possible measurement or worst quality, or the quality below which I should not think. So now let us say we have taken repeated or replicated measurements and I have multiple measurements with me. Let us say length of this room I have taken many times, 100 times, 200 times, 30 times, 1000 times, okay, but I have multiple measurements. If I take the average of those measurements, I will have higher confidence, because the errors in those individual observations are now minimized by taking the averages, because the averaging of the errors itself is cancelling each other. There are some positive errors, there are some negative errors, and there are some large errors, there are some small errors, but they are again positive and negative. So if I take large collection of data, average it, because of their characteristics following normal distribution, cancel each other. So I will have the estimate of the length as average length close to the true value. Close to, not exactly equal to, but close to the true value. I am approaching towards true value as I am increasing number of observations. So I have the confidence in my measurements of a particular variable, right? So generally we indicate this confidence by standard deviation of sample. Let's say I have taken 30 values, which I call sample and not the population. Population means all possible values of that variable. So I am taking a sample of 30 or maybe 50 or 100. So then I find out the standard deviation, and standard deviation gives me some kind of spread or some kind of confidence of that variable. And generally we represent it by 1 sigma value here. We call it 1 sigma value. Then, so this is my sample standard deviation, 1 sigma value, and generally we write mathematically by plus minus s. That means s equals to under root of average value here. So I is equal to 1 to n observations, xi my observation, x bar is the average value, divided by n minus 1. So this is s. We also call it 1 sigma value, and again it is plus minus because of the under root. When I represent some value, let us say 2.33 meter, so then I will write plus minus 1 sigma value, which is nothing but equal to s here. And this is the way we represent our measurements. Here 2.33 meters and 1 sigma will be in meters, centimeters, whatever unit I prefer to choose. So this precision is coming from observations. That means I am taking average, and again I am calculating the deviation from the average. So I can say one thing here, that precision is an internal aspect or internal to the measurement, because I am calculating the precision from the measurement itself. Let us talk about the accuracy. So accuracy is the closeness of the observations to the true value. So precision is nothing but the closeness among the observations. Closer the observations, I am more precise. Farther the observations, I am less precise. Here nothing to do with the accuracy. The accuracy is closeness of observations to the true value, and which we do not know, unfortunately. So how to estimate the accuracy then? Because we do not know the error, we do not know the true value, but we know only the observations. And the quality of observation, the confidence, we have already said it's a precision, the closeness among the observations. But now, how to estimate the error, or how to estimate the accuracy? Can we have some idea on the accuracy? This is the standard example given in many of the books, and this example has some fundamental flaw. Let us say there is a bullseye and there are 4 players, and the first player is putting his shots, 15 shots. So let us see, the first player is putting these shots. So now he has put these shots, and I find out what's the spread. I am indicating by red arrow here. So two spreads in x and y direction, right? So this is the kind of spread of the bullet shots of player 1. If I take the average value, the green dot, and now we can say what's the accuracy here? That's the accuracy. Okay, here I say that accuracy is much larger. Probably it is containing some systematic component also. Well, so that's the story of player 1. So I say that player 1 is precise because his shots are very close to each other, but he is not accurate because the average value is away from the true value, which is the center value of the bullseye. Okay. So let us take this player 2, and he puts shots this way. So this is spread values in x and y direction. This is average value, which is very close to the true value, and I say that it is accurate but not precise because you can see the precision is relative value, and it is explained by the dispersion of the various observations. This is dispersion here very high, this and this both. Now we can see player 3, his shots are like this, coming one by one. So this is his dispersion, or we can say this is the spread. Okay, I am using dispersion and spread interchangeably, don't get confused. So this is the average value shown by the green color, and now this is the accuracy here. Again, there could be possibility of some systematic component here, but I can say this player 3 is neither precise nor he is accurate. Well, you can understand that accuracy is given with respect to true value, and he is nowhere close to true value, and as a result we said he is not accurate. Moreover, his spreads of the shots are too large, so he is not precise, or we can say less precise compared to the player 1. Similarly, player 2 is also less precise compared to player 1. Player 4 is putting his shot like this. We can see that player 4 is very accurate as well as he is precise because the spread of his shots are very small. So we call him precise and accurate. Now I would like to tell the irony of this situation or the flaw in this example. In fact, as we told before, we do not know the true value, right? It is the best example to understand this concept, but true value is never known. So what about the real observation? How real observations look like if we take this example? Okay. So it will look like this. So can you tell with these observations? You can find out the precision still, but can you tell me who is most accurate here among the 4? You cannot tell any information about the accuracy because you do not know the true value. You already know the mean value, you already know that what's the precision value by standard deviation, but still you do not know the true value, and so you do not know true error, and so you do not know what's the accuracy. So that's the fundamental flaw in this example. Okay, but it's good to understand the concept. So let us derive what is accuracy now, and what's precision, and what's the relationship between the precision and accuracy. Okay, let's go ahead. Let us take a simple example of a triangle, and I have 3 angles alpha, beta and gamma in a triangle. I am observing n alpha times alpha angle, I am measuring beta angle n beta times, and n gamma times the gamma angle. So these are basically numbers. So n alpha could be 30, 40, 50, something like that, n beta could be something like that, and n gamma could be some number that is integer number basically. So I am observing each and every angle multiple times. Okay, I also know this is the kind of a condition equation exists. So what's the precision and what's the accuracy here? Precision, we have already said that the precision is nothing but the standard deviation because it is the closeness among the observations, and closeness is represented by the standard deviation, how values are away from the mean value, and that is my standard deviation. And then I take the average by n minus 1, and then we get the standard deviation. Well, so I know the precision, that's my 1 sigma value. Okay, let us look into the accuracy aspect. Okay, so I will go one by one. How do we calculate precision and how do we calculate accuracy? Okay, let us see. I take first value. So if I add v dash alpha 1 to my observation alpha 1, I will get the average value. Let us say like that. Similarly, I can write next observation alpha 2, and if I add some value v2 dash alpha, then I will get the average value of the alpha, and so on. I can write for the ith observation and I can write for the last observation, that is n alpha observation. So, I have taken n alpha number of observations here. Similarly, I have repeated the same exercise for the beta. I am writing here V1 dash beta, just note it down. That means they are quite different from each other. That means this quantity is different from this, and these quantities are also different. They are not same. Remember this thing, because they are random. Okay, so I have taken n beta number of observations here, and then further I have taken n gamma number of observations, and I have taken the observations of each angle individually. That means if I put total station at one of vertices, let us say A, B or C, and I take the observation like alpha n number of times. Well, similarly beta and gamma. Let us go ahead. Now I can take the mean value, and that you already know formulation, I am writing it here, and similarly you can find out the 1 sigma value or the standard deviation. So, this is standard deviation here of 3 values. So, these are my precisions, and I hope you agree with that. There is no doubt in that. So, then what is accuracy? Let us come to the triangle condition. It should follow this rule, but since we know that our observations are subjected to the errors, so even mean values have some error, because we have calculated mean from the sample of finite size, not of infinite size. In case of infinite observations, all errors will be cancelled because they are following normal distribution, but I know that there are some errors still remaining in the estimate of average. So, alpha bar is also subjected to plus minus 1 sigma errors. So, now let us see that alpha bar has some error, beta bar has some error, and gamma bar has some error. If I put the values of this alpha bar, beta bar and gamma bar in this relationship, I think this relationship will not be satisfied by alpha bar, beta bar and gamma bar putting together. Okay, so I introduced something called E, and let me call this quantity E here. If I add this quantity, I will get 180 degree. Yes, let me tell you, E could be negative, E could be positive. Why? Because the summation of alpha bar, beta bar and gamma bar could be more than 180 also, could be less than 180 also. So, E is having some kind of algebraic sign, plus or minus according to the summation of alpha bar, beta bar and gamma bar. So, I have put it the value of E, and then I added it, I got this 180 degree, or I can write now E equal to this one. This quantity E is error of the triangle. Remember that this condition alpha plus beta plus gamma equal to 180 degree is independent of observations for alpha, beta or gamma, and hence it is kind of an external to the measurements. I hope that you are getting the idea what is accuracy now. So, this E is the accuracy of the triangle measurement, that means of total triangular system. Okay, what is accuracy of the individual angle? Purpose is to now divide this error into 3 angles. I want to find out the error of individual angle alpha, beta and gamma. Now, let us assume for simplicity that n alpha, n beta and gamma, that is the number of observations I have taken for alpha, beta and gamma angle, they are same. That means it is equal to n. Okay, that means I have taken, let us say 100 times measurement for alpha, then I take multiple measurement which are 100 in numbers for beta, and then I take 100 measurements for gamma also. That means n alpha, n beta and n gamma are same and equal in numbers, and that is giving me some advantage. We will see in second and third lecture why, but not now. For simplicity, let us assume that they are same in numbers. So, now I can divide this error into same quantity to 3 angles. Okay, so the quantity will be E by 3 to each angle. So, let us divide this quantity by 3. So, this is what I call the error of angle alpha, error of angle beta and error of angle gamma, and which is equal to E by 3 because they have same number of observation, and hence I am assuming that they are having same amount of accuracy or same amount of error. So, this is the concept of accuracy. So, where is my reference value or where is the true value? This value 180 degree is true value, and I know that it is coming from an universal relationship, that is sum of the angles of a triangle is equal to 180 degree. I cannot challenge it, no one can challenge it. For that reason only, the accuracy is external to the measurements, while precision is internal to the measurements, because we are measuring this precision sigmas or S alpha, I can say sample standard deviation, from the measurement itself, while we are not developing this relationship. It is nothing to do with measurements. And I hope that you understood now the concept of accuracy, error, and the precision. Error is nothing but some kind of value. At the same time, accuracy is kind of limitation. So both represent each other, error and accuracy. What's error in your individual measurement, or what's the error, or what's the accuracy of the mean value? They're more or less, they are just representing with different sign. So accuracy is kind of limitation. I know what's the limitation of my measurement if I use this instrument, or if I use a total station having 2-second errors, right? So this is the meaning of 2 seconds. It is equal to E by 3. So if you want to purchase a total station now, what will you look for? Let us say that vendor claims, or manufacturer of the total station claims, that his instrument provides 2-second accuracy. So ask him to perform simple triangular experiment, where ask him to observe the angle alpha, beta and gamma at the 3 vertices of a triangle, and the triangle you can just create in open ground or even in closed room, no problem. But in closed room, while room is not very big, so let's go to the open ground, maybe a football ground, hockey ground, or basketball court. Ask him to put the total station at 3 points and observe the angle between the remaining 2 points from that point. So you measure 3 angles, alpha, beta and gamma, make a summation and try to find out what is the discrepancy or error of this summation with respect to 180 degree. Let us say it comes out to be 5 seconds total, 180 degree minus the summation of angle. So now you can confidently say that whatever vendor is claiming is correct. Why? Because if we divide 5 seconds to 3 values, that 3 angles, it will be less than 2 seconds. So now you are happy that his instrument is really giving you what he is claiming. And as I told, there is no connection between accuracy and precision, as if now we can understand. So this is what we call accuracy, and this is what we call precision. You already understand both of the things now. Don't commit any mistake on this front. What's the accuracy? What is the precision? Well, it is possible if there are no systematic errors, and if there are no blunders, then in the presence of only random errors, the precision or the sigma value can represent the accuracy also. That's a different matter. But as if now both are different. Now, what we call the accuracy E by 3 of each angle, okay, then we also call them residual, and we write with the help of V. V alpha is a residual to the alpha angle such that it is making it accurate. That means if I add alpha plus V alpha, so whatever value comes, that is we call adjusted value. So I can write here the adjusted value of alpha is nothing but alpha bar plus V alpha. Similarly, beta is the adjusted value of beta, beta bar plus V beta. Gamma, the adjusted value here is gamma bar plus V gamma. Now I write generally adjusted values of the alpha, beta and gamma. So alpha A, beta A and gamma A. Now you put the relationship alpha plus beta plus gamma with alpha A, beta A and the gamma A, which are adjusted values of alpha, beta and gamma, you will get 180 degree. And now you have also estimated these V's, so you know what's the accuracy. So these are basically accuracy of the angle, V alpha, and we represent it by called residual or accuracy. Generally we write as a residual here like this, V alpha, V beta, V gamma equal to this one. Moreover, if you notice, as I told earlier also, this error E by 3 in each angle could be positive, could be negative, depending on the summation of alpha, beta and gamma in the condition equation of triangle. So let us make some other estimate. Let us make them square. That means they will become positive, and then add them up. So V alpha square plus V beta square plus V gamma square, and now divide it by degree of freedom, and then take a root. You will get E by root 3, provided residual are equal. In this particular case, we will get E by root 3, and this is called the standard error of unit weight. Remember, we have different weights of the observation in basic surveying. So now I am saying that, let us say that there is a weight equal to 1, and what is the corresponding error to that? And that is this error, and we call it the error of unit weight. Okay, so yes, this is called H0 here, and it is calculated value, that's why I am writing H0. But if it is estimated, we generally write it by sigma 0, and it is estimated one. The estimated value of error of unit weight, and this one H0 is nothing but the calculated value after complete adjustment process is over. Now, what is the degree of freedom? If you see, in case of triangle, there we have one condition equation, alpha plus beta plus gamma equal to 180 degree. Now, if I observe any two angle, I can find out the third angle automatically using the condition equation. So basically, I have the number of parameters or number of unknowns is just equal to 2 because I have one condition equation. Using the condition equation, if I have the values of 2, I can find out the third value. Or you can choose any of the angle as a third angle. You observe two angle, find out the third angle using condition equation. So I can say that the number of parameters are equal to 2, any two angles. Number of variables measured, I measure all three angles here. So they are basically three variables. So if I put 3 minus 2 is equal to degree of freedom. That means I have a freedom to calculate one variable, and that is why here degree of freedom is equal to 3 minus 2 equal to 1. Now you got what's the idea of error of unit weight, H0. So let us start the error propagation, where errors are random, errors are small. Remember what's the meaning of errors are small? I have taken an observation of 2.33 meter to measure the length of this room, and I find out that there could be error of 1 centimeter, 2 centimeter, something very small. That's the meaning here. They are random also. Okay, they follow normal distribution, and if I take multiple measurements, which means if I am taking the length of this room multiple times, so whatever errors occurring in each observation, these errors are mutually independent of each other. That means the observation 1 have some error, let us say E1, and observation 2 of the same length has error E2, but E1 and E2 are coming independently, and there is no connection between the two. That means E1 can be any value, E2 can be any value, but they are although following normal distribution, but they are occurring randomly and independently, and they are not correlated. This is my assumption here. Now I want to calculate what is the error in the area if I measure the width and length with certain error. Okay, so the length error is, let's say, sigma L, and the width error is called sigma W, if L and W are representing the length and width of this room. So let us calculate what could be the possible value of the error that is propagated into the area, which is multiplication of L and W. So let us take that one. Okay, so I have written here in the screen what would be the error in the dependent variable, which is area of this room, given input measurements and their precision values. Okay, so let us take an example. I am writing here area equal to L into W. Fine. So what is the error into A? That means I want to find out what is the value of sigma A. Okay, so what will I do? I use the law of error propagation. Okay, and I am giving you a simple idea. There is a formula for that. I am writing that formula. Okay, so I am writing here, let us say that I want to find out the sigma A, which I am writing as, let us say, this sigma A equal to dA by dL into sigma L square, both are square, plus dA by dW square sigma W square, where these two are one sigma value. You got the idea from basic surveying, although I am using this symbol. Now I am giving you other formula for the same thing, but it has multiple applications and it is quite different from this formula. So we are not going to use this formula anymore in our higher surveying. Rather, we are going to use slightly different and comprehensive formula, and the formula is given by sigma A is equal to J sigma JT, where I will write sigma LW. What is the sigma LW and what is J? J is nothing but the Jacobian matrix of A with respect to L and W, right. So, JT is transpose matrix of J and sigma LW is covariance variance matrix of L and W. So, what is the meaning here? This is the meaning here, that sigma L square, sigma W square, sigma LW and sigma LW. So, these two values, this and this, are same and equal and representing the covariance of errors of the measurements in L and W. I can also write like this matrix, sigma L square, sigma W square, sigma LW, sigma LW. Well, sigma L is precision of the measurements of length and sigma W is precision of measurements of width. Now, when we observe something in the field, we say that in general from the field observations, we can assume that errors are independent and hence we have sigma LW equal to 0, or this matrix is a diagonal matrix because this is equal to 0, this is also equal to 0. So, now if we put the values here in this formula, I should get the sigma A, that is the error propagated in area A. Okay, what about the J matrix here? J is given by dA by dL and dA by dW. In the next lecture, we are going to learn the law of error propagation its full length. We will solve a couple of examples and we will see what is the effect of variance covariance and how variances, that sigma L square, propagates into the dependent variable, or rather I can estimate the error of the dependent variable by this law of error propagation, provided I know the error of the input or the fundamental measurements, right. So, we will meet in the next lecture. Thank you very much.